Hello everyone, I hope everyone's having a great day when they start watching this video. Today we're going to be learning about heat and phase changes. So we learned way back when we started this whole overall unit about thermal expansion, thermal heat, about phase changes. But we're going to be talking about how to calculate or how to find how much heat, how much energy goes into each one of these. But first we just want to kind of learn a little bit more about what's going on in each of these phase changes. So some questions as always to get us kind of thinking are what are our four types of phase changes? So I'm curious if you guys could remember what they are. What the ones that we've talked about are solid, liquid, gas, and plasma. Plasma is a kind of a special case, but the three main ones are solid, liquid, and gas. Those are the ones we're going to be working with today. And then does it require heat or release heat to change from a liquid to a gas? So if we have water, for example, do we need to put in heat to take it from a liquid water to gas, or does it release water? And of course, it requires heat. So I think of when I'm boiling water on the stove, maybe I'm cooking pasta and I needed to warm up water, or anything that we need to have hot water for. It always requires heat. We got to put heat in to to change our water from a liquid to a gas. So we'll be talking about some of that today. So by the end of our presentation, we want to be able to describe each type of phase change. We have special words for if we're going from solid to liquid, liquid to gas. And then we want to understand how it requires energy, or how it requires energy to change phases. So we want to understand how the energy is changing as we're going through a phase change. So here's our video. It'll be linked in our classroom as always, so please pause this video to go watch this one. It does a really good job explaining things. It's a short video today, so just some review. So we've learned about our four phases of matter: solid, liquid, gas, and plasma. But each changing of states have special names to it. Those are the new things that we're going to be learning today. So if we have a gas going to a liquid, it's called condensation. If we have a liquid going to a solid, we have freezing. If we have a solid going, that should be solid to gas. My apologies, solid to gas. It's sublimation. If it's gas to solid, it's deposition. If it's solid to liquid, it's melting. And liquid to gas, it's evaporation. So we might have heard some of these before. I think of freezing and melting especially are common ones I hear, because we have a lot of the times we have maybe an ice cube melting to go to liquid, or liquid water freezing to go to a solid. I've also heard of evaporation and condensation just when I've learned about the water cycle, but maybe those are new words. And then sublimation and deposition are definitely ones that aren't as common, but these are the verbs or the words that we use to describe it. So instead of just saying, there was a phase change for a substance that went from solid to liquid, we can just say that substance melted. So it's a lot shorter, easier way to say it, but these might be some new words for you guys. I would definitely write this down in your notes. Take some time. It just does a good job of explaining each one of these words rather than writing out the words out. You can see it in a nice table here. So if I look at solid and this arrow points to liquid, that means if we go from solid to liquid, we're melting. This is the exact opposite. If we go from liquid to solid, it's freezing. And it's the same way for all those. So it's a good way to visualize what these words mean rather than write them down. I at least like to see a picture rather than just have words. So energy and phase changes. So there must be energy added or removed in each of these phase changes. Every time we are changing from a liquid to a solid, a gas to a solid, any one of these changes, energy is being moved somewhere. So remember that more energy means more movement of particles. So for example, my solid, maybe the desk that my computer's on right now, my particles are moving a lot less than my gas particles, which are bouncing all around. And we've seen a simulation which kind of showed us how that changes, or how the molecules themselves look. So which phase needs energy? So my question is, so which phase needs energy, what change do you need to put energy in to have? So if we're freezing something, are we putting energy in, or are we taking energy out? And by taking energy out, we're having our molecules move less. So if we take energy out, our molecules are moving less. If we're putting energy in, our molecules are going to move more. So our molecules are going to move more as we go from solid to liquid, as we go from liquid to gas, or from solid to gas. So those 3 times are when we need to put energy in. So for melting, for evaporation, and sublimation. And then the exact opposite is which phases give off energy, or we don't need to put energy into. So naturally, as water cools down, as it moves less, as our molecules move less, we have condensation. As our molecules move even more or less, we have freezing or deposition. So the question is, how much energy is changed here? How much energy is it given off, or how much energy do we need to put in? We will learn about more, but we see this good little picture. I like to show this because it says our heat taken from the environment. So anytime heat is taken from the environment, in terms of, for example, ice going to liquid, maybe the sun is melting it, and liquid going to vapor, and then heat released from the environment is the exact opposite. So just another way to think about it. So what we have, we're going to learn a couple new terms here. So this idea is that every time we go through a phase change, it takes energy to change from a liquid to a gas to a liquid, or a solid. Any one of those terms we just learned, it takes energy to go through. So we have 3 terms here. We have the molar heat of fusion, which is shown as delta H fusion, the molar heat of vaporization, delta H vape, and the molar heat of sublimation, delta H sub. So this idea, this term, is the exact amount of heat absorbed from 1 mole of a substance as it's changed from a solid to a liquid. So we can see right here, we have our latent heat of fusion, or molar heat of fusion. It's the same thing as we go from solid to liquid. As we go from liquid to vapor, we're vaporizing. So our molar heat of vaporization is the heat absorbed by 1 mole of a substance as it changes from a liquid to a gas. And then sublimation is going from solid to a gas or a vapor. Sublimation, so it's the heat absorbed by 1 mole of a substance as it goes from from a solid to a gas. So I think this phase change energy chart is really important. I think it illustrates a very important point, especially as we are going to start doing calculations about this. So up until this point, we've learned how to do calculations for how much heat it takes to maybe raise water from 20 degrees Celsius to 80 degrees Celsius. And that is Q is equal to MC Cp delta T, or the heat is equal to our mass times our specific heat times the change in temperature. So anytime we had a change in temperature in a liquid, we could find the amount of heat that it required. Or maybe even in a solid, we could find the amount of heat that was required or given to raise that temperature. But as we go through phase changes, we have to account for the amount of heat it takes to change each one of those molecules just a little bit. Each one of those molecules into a different phase. So we can see here on our temperature scale that as we go up, if we're starting at ice and it's really, really cold, it's maybe minus 20 degrees Celsius, we can heat it up all the way to 0. But at 0 degrees Celsius, ice turns to water. But we have heat that's getting put in. This is what this part of the graph is showing, that we are continuing to put heat in without a temperature change. So we have to put more and more heat in without a temperature change, because that heat is going to help change all of our molecules from a solid to a liquid. And then we're going to go all the way up again. Once we have all of our, right here, we have all of our molecules in this liquid form, but they're all at 0 degrees Celsius. So to go from this part to this part, all we did was change, all our energy went to changing our phase, and then we go up our chart again. We're increasing our temperature of our water, our liquid water. Our liquid water is getting increasing temperature, and then we reach 100 degrees Celsius. At 100 degrees Celsius, our water starts to evaporate. So we're going to put more and more energy in to change our liquid water to a gas or a vapor, but none of our gas is going to increase in temperature. All of our energy is going towards creating a gas. All our liquid is going into a gas. And so once we get to here, at this point in our table, we're going to be able to start increasing. Everything's in the gas phase, and now we can increase the temperature in the gas phase. So these two straight lines are very, very important, because these are our phase changes. It's a phase change anytime we have a straight line here, because all of our energy is going into our phase change. It's not going into raising our temperature. So I made a little simplified one here. I think it's helpful to write down examples rather than words sometimes. So this is an example that we could write in our notes. You can always pause the video and then sketch this out for yourself. But our big takeaways from today is we have special words to describe each type of phase change. We have sublimation, I'll read them this way. We have melting, freezing, evaporation, condensation, sublimation, and deposition. And it takes heat to change phases. So the amount of heat needed for each phase change is found using our delta H fusion, delta H vap, or delta H sub. So that's just the start of thermal energy during phase changes. We're going to go into how to calculate how much energy is removed or how much energy is put in during a phase change coming up. But this is just kind of the, you could call it the base layer or the foundation of what we're going to be learning about. So I hope that made sense. I hope that you guys understand, but if you have any questions, as always, please let me know.